again for having me. Today we're going to talk about the diffusion capacity of the lung for carbon monoxide. And it is, I'm going to give a warning because it is a topic that is difficult to teach our pulmonary fellows. And I imagine that, with the language and translations and those things, it will probably be difficult to communicate to this group. So I appreciate your patience with it, and hopefully you find it interesting. But it is a challenging topic, even for us that are, doing this in the field. So, okay, so the outline of the talk today, we're going to talk about the technique, the physiology underlying the measurement, and that is the vast majority, really, is understanding what is actually being measured and how it works and why, what is a low diffusion capacity mean physiologically. The rest of the stuff, memorizing which diseases are associated with what, these are all things that naturally follow from the physiology. And so they're not really as important as understanding how it works. So, we talk about the calculation of the diffusing capacity, the transfer coefficient of the lung, the measurement of the DLCO, and the clinical usefulness of it. Now, the context is important. Where does this fit in the context of measuring lung performance? And I like to think that the lungs have two main jobs. They move air and they exchange gases, right? So when we think of respiratory failure, we have, hypoxic and hypercapnic respiratory failure, which are, failures of usually diffusion or VQ matching, and then also with moving air, the pump function of the lung. The other lung function tests, so spirometry is probably the most useful single pulmonary function test. And, that's just tells us how fast we can move air, how big of a breath you can take, several other things. But and then plethysmography, which I gave the lecture on a few weeks back, tells us about the size of the lungs, how much air is left, after you exhale. So what is the total lung capacity? And a few other things it can tell us as well. Both of those are more on the side of moving air, how much air is in the lungs. The DLCO test, which I think in Europe is called the TLCO, or the transfer factor of the lung for carbon monoxide, it tries to tell us something about gas exchange in the lungs. So it's the second part of that. And so it's part of pulmonary function testing, and it tells us a little bit more about the gas exchange bit. The history of the test, well, it's been around for a long time, almost 100 years. And as I mentioned before, I think in Europe, and I guess you guys can correct me, but I think it's called the transfer factor in Europe. And that's probably a better term, actually. And in the US, it's called the diffusion capacity. So in 1915, Marie Crowe developed this method of the single breath uptake of carbon monoxide in the lung, and that work is still how it's basically done today. In 1957, this was modified by Ogilvy's group, and they standardized how they measure, and they used a tracer gas to determine another measure at the same time. And then in 1987, there were, published international standards, and then they were updated in 2005 and 17 by the American Thoracic Society and the European Respiratory Society. Okay. So while it's been around for a long time, there have been some technical changes and standardization that have occurred over the years, and it's remained very confusing, I think, for people. So in one graph, this is kind of what's happening, and I don't expect from this graph to understand, but when we move forward, hopefully by the end, we can understand it together. Fundamentally, the test output is the product of two separate and simultaneous measurements that are taken at a breath hold at full inflation. So in practice, your patient is sitting in the machine with a good seal over the tube that they're breathing in this gas through. And they take a full breath to maximal lung capacity. And the air that they breathe in has a very small percentage of carbon monoxide, 0.3%, and then a very small percentage of tracer gas, either helium or methane, I think typically methane these days. And so the machine, when they start to take their deep breath in, opens the shutter for this tracer gas, and the patient takes their breath in and they hold it for 10 seconds, and then they exhale. And when they exhale, the machine then measures the concentration of the two gases. And the tracer gas, is a gas that is not absorbed by the body. So all that happens when you inhale and exhale it is that when you inhale it, you inhale a known volume, the machine measures it, and it redistributes in the lungs, and it becomes a lower concentration. So you can see that, the initial concentration drops significantly, but then while you're holding your breath in the lungs, it maintains constant, and then you exhale. And when you exhale, there's a sensor that measures the concentration. And so essentially, because you know the inhaled volume, you know the inhaled concentration, and you measure the exhaled concentration, you can calculate the alveolar volume, the volume of the lung that is participating in this breath. So you find a way to measure lung volume, kind of alveolar volume, and then at the same time, there is another gas, which is this carbon monoxide. And this gas is, the concentration that you breathe in, and then similarly, you measure the concentration when you exhale. And this gas is absorbed, and that rate of absorption here, the slope of this line, tells us something about how efficient the lung function is. And it's important to know the alveolar volume because obviously if you have a bigger breath, you will have more diffusion than if you have a smaller breath. So this is why you need to know how big of a breath, how big the lungs are, basically. So that's why you have the two measurements. So the test measures two things: the rate of carbon monoxide uptake, and that is this dotted line here. And it's calculated from the difference between the initial carbon monoxide and the final carbon monoxide. And then it also measures what's called the accessible alveolar volume, and that's this tracer gas. Whoops, let me go back. This tracer gas here that is used to just by changing in concentration is used to estimate the accessible alveolar volume. So I'm guessing that's confusing. It's confusing to me even, but this is really how it works. And I think by the end of this, hopefully this becomes a little bit more clear. So let's start with some physiology. And the first thing is going to be, how does a gas diffuse from the alveolus in the lung into the capillary? And that is modeled by Fick's law of diffusion. So on the left here, sorry, here you can see my mouse. On the left here, you can see a diagram which represents the alveolar wall, so one alveolus, one unit in the lungs. And this is the wall of this alveolus. and then here is the capillary wall, and inside here is blood. And there is some concentration of oxygen inside the lung, which then diffuses into the blood. And in this maneuver, there's some concentration of carbon monoxide in the lung, which then diffuses into the blood. And obviously, this diffusion is going to depend on the pressure difference between these gases and something about the thickness of this overall membrane. And also, of course, you know, how much of this there is. If there's more surface area in contact than less, then there will be more. So in equation format, Fick's law is displayed like this. The flow of gas, which is this V dot gas, is proportional to the area. Okay, so that's the area, the surface area that's in contact. And it's inversely proportional to the thickness, that's, you know, how thick this membrane is, multiplied by some constant, and we'll go over that constant, and then multiplied by the pressure difference between these two places for the gas. This diffusion constant is itself dependent on the solubility of the gas in blood, and it's inversely proportional to the square root of the molecular weight. So this part here is Fick's law of diffusion. Oops, let me go back. Is Fick's law of diffusion. And what has been done to simplify things is, so we recognize that in the lungs, we don't really know the surface area of the lung and the thickness of the lung. But you can imagine if you take the whole lung unit, this is some constant. And this K is dependent on the solubility of the gas, carbon monoxide in this case, and the molecular weight. So this all can be combined into one term. So this A over T times K here is then just combined and called the diffusion capacity, or DL. And it's the diffusion capacity of the lung, and we can label that as for carbon monoxide or for any gas, but for our purposes, we use carbon monoxide. So the flow of carbon monoxide is then proportional to the diffusion capacity of the lung times the pressure difference. And that's Fick's law of diffusion. Now, I think the European moniker of the transfer capacity is probably a little bit better, because it's more than diffusion. We're really transferring carbon monoxide from the lung to the blood. But this is a change in terminology. Now, the one thing you may point out, you know, for those of you that, if you remember some of the basic physics, this diffusion capacity is a capacity. If you multiply this times the pressure difference, this is very similar to Ohm's law, and this capacity is actually the inverse of the resistance. So this will become important later, but this diffusion capacity is a capacity, and you can actually model it like in Ohm's law. Okay, so we have a few equations that unfortunately I think are necessary, and I've explained them a little bit on the last page, but we have the flow of whichever gas we choose is, like I said before, proportional to the area that is of the membrane divided by the thickness times this constant and the pressure difference. This constant here is again is the solubility divided by the square of molecular weight. And excuse me, if we substitute this DL, diffusion capacity of the lung, for this term here, and then we solve for DL, we get that the diffusion capacity of the lung for whichever gas is equal to the flow of that gas, or the transfer of that gas, divided by the pressure difference here. Okay? So all I've done here is take, you know, this, I've called this A over T times K, I've called that the diffusion capacity. And since we're talking about the lung, it's the diffusion capacity of the lung. And then I've solved for it. And that's how I get this. I've solved for it with this equation. So fairly straightforward. But then the question is, why are we using carbon monoxide? Well, we need to go back to what we're trying to get at. We know something about how the lung moves air and how big it is, but we want to get a sense of how well the membranes are working, how well you can absorb gas, right? So carbon monoxide has some properties that make it attractive for that. And the main thing is that carbon monoxide is a gas that is diffusion limited. So this picture here, this diagram, let me explain. So this part here represents one alveolus, so a terminal unit on the lung, and one capillary here. And so the blood comes in the capillary here and then exits here. And if you think about, for example, oxygen, blood comes in deoxygenated, and then it equilibrates and then leaves oxygenated. But if you look at physically on the capillary, how fast this equilibration happens, that is displayed in this graph here. So on the y-axis, we have the partial pressure of oxygen. And on the x-axis is the time spent in the capillary. So you can see that the oxygen goes from deoxygenated to oxygenated relatively quickly within the first third or so of the capillary under normal conditions. So as the red blood cell is moving along this capillary, in a normal healthy person with normal cardiac output, it's deoxygenated here. But by the time it gets to here, it is fully oxygenated. And this remainder of the unit is really just a physiological cushion. So this is excess that can be used if you're exercising or something like that. So oxygen is because of this called perfusion limited. Carbon monoxide, on the other hand, does not reach an equilibrium along this part here. It just slowly rises over time, and it is diffusion limited, therefore. So the fact that it is diffusion limited allows us to get some better information about the diffusion properties of this alveolar capillary unit, and really for the whole lungs, the entire summation of all the alveolar capillary units of the lung. So that's why we use carbon monoxide. It's diffusion limited. The other thing that's excellent about carbon monoxide is that when it is absorbed, when it diffuses into the blood, it is fairly immediately and tightly bound to hemoglobin. So the concentration of the carbon monoxide in the capillary blood remains fairly low because it is mainly bound to the hemoglobin. So going back to our equations, and this is a restatement of what we saw before, the diffusion capacity of the lung is equal to the uptake of the gas, the flow of the gas, the transfer of the gas, divided by the change in pressure. And because carbon monoxide binds very strongly to hemoglobin, the partial pressure of carbon monoxide in the capillary is very small compared to what's in the alveolus. So as a good estimation, you can ignore this P2 when you're calculating the diffusion capacity of the lung. And that's again because we chose carbon monoxide. So this simplifies then to the diffusion capacity of the lung for carbon monoxide is equal to the flow, the uptake of the gas, divided by the concentration, the partial pressure in the alveolus of carbon monoxide. So this is just a simplification, and it's valid because we use carbon monoxide. Well, then how do you measure the transfer of this gas? So like I said at the beginning, the patient is attached to a machine and they breathe normally with a tight seal around a tube that has gas of normal concentrations. And then the patient is instructed, whoops, go back. The patient is instructed to exhale and then inhale to the maximal volume and hold breath for 10 seconds and then exhale slowly. And when they do this inhalation, the shutter opens and the patient then breathes a mixture of not just room air, but oxygen, nitrogen, and this fixed concentration of carbon monoxide, which is 0.3% typically. And then a tracer gas, historically helium, but I think these days everyone uses methane. And what is fundamentally measured by the machine is this change in concentration of carbon monoxide, and then using this tracer gas, something called the accessible alveolar volume. And these two things measured will tell us the DLCO and are helpful in determining, in teasing out maybe what's wrong with someone's lungs. So the maneuver, you have an inhalation to maximum volume, a breath hold for about 10 seconds, and then an exhalation period. And during this point, some of the gas is sampled by the machine to measure the concentration. And that's displayed in this picture here. So you can see, for example, this inhalation to full and this breath hold for about 10 seconds. And then the exhalation, there is a tracer gas and carbon monoxide here. And the machine will measure the concentration of these things during the exhalation period. Let's go back to some of the math then. So we're trying to figure out how do we calculate how much flow there is. And what we need to know is what's the volume of carbon monoxide in the alveolar space? Well, that's simply the alveolar volume multiplied by the fraction of carbon monoxide. And at a constant volume, the transfer of carbon monoxide from the lungs to the blood will be displayed by this, which is, there should be a dot here, but the flow of carbon monoxide is going to be equal to the alveolar volume multiplied by the change in concentration of carbon monoxide divided by the change in time, so the length of the breath hold maneuver. Now, this change in concentration is a simplistic way of looking at it. When we measure things, we think about the partial pressure of carbon monoxide. And so there is a factor of barometric pressure minus water vapor pressure that we use to correct this. But this is a technical thing that probably doesn't matter too much for our understanding of the physiology. So the complete solution is that the derivative, the change of the alveolar volume multiplied by the fraction, so this is again, this represents the volume, is equal to the DLCO multiplied by this fraction of carbon monoxide times the barometric pressure minus the water vapor pressure. This part here essentially gives us the, one second. Oh, my kids have gotten me sick. Okay, so this part here essentially represents the partial pressure of carbon monoxide. If you solve this, for DLCO, you get that the DLCO is equal to the alveolar volume divided by the time of the breath hold maneuver, multiplied by this, pressure in the lungs. You subtract the water vapor pressure from that, and then multiplied by the natural logarithm of the change in concentration, initial and at the final time of the breath hold. So this is the final equation here. And this is how the machine will spit out the DLCO number. So this T is the time of breath hold, and this is very simple. You know how long the patient holds their breath. That's measured on the machine. Barometric pressure is just the pressure at whatever altitude you're on. And then the water vapor pressure is known. The alveolar volume has to be measured. And so this alveolar volume is measured using the tracer gas, which we'll talk about on the next, I think the next page or 2 pages from now. And then the natural log of the change in the concentration, essentially, of carbon monoxide at the initial and then the final. So in the end, it is 2 simultaneous measurements, like I said at the beginning. One is the alveolar volume, and the second is the uptake of carbon monoxide. And to measure the alveolar volume, we use this tracer gas and the change in concentration. So patient inhales, so the tracer gas maneuver is fairly simple. The patient inhales a known concentration of helium or methane, and since we're measuring as they inhale, we know what kind of breath size they have. And they hold their breath, and this gas then redistributes in the lungs during that breath hold. And therefore, the concentration of the gas decreases. And then the patient exhales, and the machine measures the concentration of the gas. And technically, it wastes about a little bit of it to get rid of the dead space volume. And then we know, simply that if you have initial concentration times volume, there's conservation of mass. So the initial concentration times volume is going to be equal to the concentration at time 2 times the volume 2. And we know the initial concentration. We measure how big of a breath they take in, and then we measure the second concentration. So this volume 2 is what is called the accessible alveolar volume. And it's simple to calculate for, but this represents how much of the alveoli are actually participating in this gas exchange maneuver. And that's how we index this carbon monoxide, this diffusion capacity. So the slope of this line is the transfer factor for carbon monoxide. Now, so that's the measurement portion, but in order to understand what's wrong with the whole unit, we have to look at the lung unit in another way. And that is gas transfer. So that is looking at gas transfer as the sum of 2 resistances. So these 2 guys, Ruffton and Forrester, they modeled the diffusion capacity of the lung as the sum of 2 components. So in order for the gas, whichever gas, oxygen, carbon dioxide, anything, to get into to be absorbed, it has to cross the alveolar wall, and then it has to interact and get absorbed and uptaken by the red blood cell itself. Okay? So there's 2 components. There is a resistance associated with the membrane, and a resistance associated with the rate reaction of the gas carbon monoxide with hemoglobin. And also, there's this capillary blood amount, this volume. So we can imagine that if the membrane is thicker, it will be harder for gas to be absorbed. This theta is this reaction rate of carbon monoxide with hemoglobin. So this is relatively constant. But this VC is the volume of capillary blood. So if there's more blood around, then you will be able to uptake more. So you have to overcome these two resistances. Now, as we mentioned before, the diffusion capacity is a capacity. The inverse of it is a resistance, similar to in Ohm's law from physics. And these two resistances will sum together, because they're in series, to be equal to the associated resistance of the diffusion capacity, dL. So on the bottom here, we have 1 over this dL, which is the diffusion capacity of the lung, is equal to 1 over dm. This is the membrane kind of component of resistance. And then 1 over this theta times Vc. And this theta represents the rate reaction of carbon monoxide with the hemoglobin. And then this Vc represents the volume of the capillary blood. So ultimately, the things that are going to affect the diffusion capacity of the lung include aberrations of this membrane, but also aberrations here with the volume of blood, or if for any reason there's a problem with the rate reaction of carbon monoxide with the hemoglobin. And rarely this can happen. So, for example, if a patient is a smoker, then they may have some carbon monoxide build up naturally. We know that that's normal. And that makes this rate reaction slower, actually. So there is some real world impact on this theta number, too. So restating it, this 1 over DLCO. So DLCO is a capacitance, 1 over DLCO is a resistance. Is equal to 1 over this diffusion of the membrane plus this 1 over theta times the volume of capillary blood. And if the math doesn't make sense, that's fine. But all that we really need to know, practically speaking, is that the DLCO is then affected by issues with the membrane, issues with the rate of reaction of carbon monoxide with hemoglobin, that's this theta, the hemoglobin concentration, the volume of capillary blood. And that's what we get from the Rothman-Forster equation. So graphically, you can look at these terminal bronchial units in different diseases and get a sense for what may happen with the diffusion capacity, or the diffusion capacity divided by the volume, which is this KCO number. And on A, you have a normal unit where you have a terminal bronchial, a bunch of alveoli, and it's been cut open so you can kind of see this looks normal. You can see the normal blue capillaries coming in and then red capillaries leaving. And this is meant to be the norm. In B, you have emphysema, and so you have destruction of a lot of these air capillary interfaces with a low accessible alveolar volume and less blood flow, you can see here. In C, in interstitial lung diseases, you can see the membranes are much thicker here, and there's destruction of this capillary interface. In D, you have lung resection, where the blood supply is actually, if anything, you can see the blood supply, these are meant to be somewhat dilated compared to this one. And but you lose some alveolar units. So in D, the DLCO decreases, but the efficiency, which is the DLCO per unit volume, kind of the KCO, actually is pretty good. And then in E, you have vasculitis without hemorrhage. So then the vessels are much, much smaller, you can see here. But if you have hemorrhage, then you have a lot of blood in the alveoli, and this will cause a massive increase in DLCO because the volume of blood goes up. Finally, you have F, which is congestive heart failure, where everything is swollen there, including the membranes. So what we've shown so far is that you can measure the carbon monoxide change in concentration in a single breath hold maneuver, and that change in concentration, in addition to the alveolar volume, can be used to calculate how much of the gas is transferred or diffused over time. And if these are abnormal, it implies there's something wrong with gas exchange. And you can further, think about it according to the Ruffman-Forster equation. There's something wrong with diffusion or reaction with the hemoglobin or the capillary blood supply. So something is wrong with that alveolar capillary units. And the information that you get are really two numbers of significance: the DLCO, which is this diffusion capacity, which is that? There it is. Diffusion capacity for carbon monoxide, and this DLCO over the alveolar volume, which is also called the KCO. And this you can think of as kind of an efficiency of the lung. So the initial one is just how much can you move, how much can you transfer. The second one is for that alveolar volume that you did the maneuver at, how much is transferred. And so it gives you some idea of efficiency of the unit. And there are different clinically relevant causes of decreased, efficiency of the lung units. And you can break them further down by how much alveolar volume you have. And these are probably less important to know. The concepts preceding are probably more important. So things like microvascular destruction or remodeling seen in idiopathic pulmonary hypertension or vasculitis or hepatopulmonary syndrome or pulmonary AVMs. This will cause a decreased DLCO over VA with a normal alveolar volume. With the reduced alveolar volume, you have destruction, which can occur in interstitial lung diseases or in emphysema with low accessible alveolar volume. So that's like with air trapping. And then finally, things like microvascular destruction in bronchiolitis obliterans or chronic heart failure. And then, high causes of DLCO or VA, increased blood flow or shunts, low breath volumes. If you remove a significant portion of the lung, then as we showed in the one of the previous graphs, the blood supply is increased to the other. And so the efficiency of that unit actually goes up. So the DLCO over VA goes up. And then if you have blood that leaks into the if you have alveolar hemorrhage, then carbon monoxide will be, absorbed much higher. And so you have a increase in efficiency of absorption, but it doesn't mean your lungs are okay. It's actually, abnormal. So how do you use this test? It's part of the workup for dyspnea. When we see patients in pulmonary clinic, if they have unexplained dyspnea, it can suggest different diseases, but it rarely is used to diagnose a specific disease. So, we frequently have people that have shortness of breath, and shortness of breath is one of those annoying diseases to try and, figure out, because most of the time it's nothing that is, it's, poor cardiorespiratory fitness. People are idle. They're not, they're overweight, etc. And the problem is that, you can have significant disease that results in dyspnea, or you can just have, physical deconditioning. Now, there's a lot of tests that can be done for shortness of breath. You can look at the lungs with X-ray, with CT scan. You can exercise somebody and measure their, their VO2 max, their oxygen consumption. You can do echocardiograms. You can even do things like exercise people and do invasive right heart cath while they're exercising to see what their hemodynamics show. But all of these things, are generally not done. So, where do we where do we start? And so in a dyspnea clinic, obviously a careful history and exam, and then usually a full pulmonary function test to say, well, globally speaking, the lungs are moving air okay, and they're exchanging gases okay, then that's good. But if there is some abnormality seen, it may prompt further investigation of certain diseases. So that's really how we use it in unexplained dyspnea. The other piece is that we follow it because it is a marker of severity of lung disease. So we follow it in interstitial lung diseases. And if it is dropping, it may be a sign that someone is having an exacerbation of their interstitial lung disease, or, it's getting worse, and it may trigger changes in treatment plans. There are a lot of pitfalls with this test and some warnings. So, it requires that a patient can follow direction well, and that the RT knows what they're doing. It's still a pretty easy test to do, but the patient has to make a good effort. And I can't stress this enough. They have to inhale to maximal inspiration. Because if they don't inhale to maximal inspiration, the DLCO will be decreased. But it doesn't mean that they're abnormal. It means that they just didn't take a full breath. So we, at the same time, do a spirometry to see how big of a breath can they really take. And it has to be around 90% plus of that. So if they don't make this good effort, then this test is, kind of useless. There is a lot of quality grading, acceptability, repeatability criteria that need to be met. Because I didn't want to put you all to sleep, I didn't include that part in this talk. It is all just like technical things, but they are important, and so you need a good system in place that ensures that you're doing the test properly, you're interpreting it properly, you're looking for errors in the graphs, etc. And then you need a good pulmonologist to review the data. So it's job security for me. And that's it. These are the main sources. I think they're pretty good sources. The John West, respiratory physiology is kind of the Bible for respiratory physiology. It's a textbook, but I've included it there. And then a few of these other articles here. Okay, questions, if any.
Thank you, Adam. Colleagues, do you have questions? Anton?
No, I don't have questions. Thank you. Very interesting lecture.
Okay, but interesting, but so difficult, maybe, yes, because a lot of physics questions. So my colleagues, yes, without enthusiasm, because they need time to.
I was a little worried just because it is kind of dense, and I imagine that with the language barrier, it's probably hard to follow what I'm saying. I hope that at least some of it is interesting.
Yes, it's true. I have one question. I don't understand what kind of equipment should help us to check this parameter.
Oh, it's part of when we buy we buy basically the whole pulmonary function test equipment from a variety of companies, but it's all sold in like one package. So basically, usually you buy the spirometry unit plus the plethysmography unit, which we talked about, last lecture, and then also this DLCO equipment, which includes carbon monoxide and methane gas for the maneuver. So that part is more of like you contract with some company that provides the supplies for you.
So it is not specific simple device. Yes, it's spirometer, for example, that includes this check of these parameters. Is it
yes,
correct?
spirometry doesn't include this one. It's a separate device, but it's commercially available. There's many different systems, but the best systems, at least here, they cost unbelievable amount of money. But they're separate, several different systems, but the best ones are probably the single breath DLCO maneuvers that use these devices. So, you know, for I think our PFT machines, you know, including the plethysmography, and I mean, like, I think they spend like $100,000 on these things for the equipment, but we buy them from some company. I think the company is actually German, the one that we buy from, but there's multiple different companies that sell them. So.
Thank you, Adam. It was interesting but difficult.
Thank you so
We
much.
appreciate you. Okay,
All
thank
right.
you.
Take care.
Bye.